But now observe that if you have anything like a moderate rotation, okay, Q turns out to be pretty different from the isotropic tensor. Okay, so let's suppose now that we have a rotation in which okay, let's suppose that we have our bases E1, E2, E3. Okay, so let's suppose that we have a rotation only in the E1, E2 plane. Okay, so we have this. I'm going to rotate it essentially about the E3 axis, right? So I'm saying that the rotation is about the E3 axis. All right, and let's suppose that these rotations in the E1, E2 plane about that E3 axis are of you know, we have a rotation of angle theta. Okay, so consider the following, right? So we have okay, consider that you have a body. Now I'm going to draw the axes right inside here, right, or just outside here. Right, so we have E1, E2, E3. We're talking of a rotation about that axis, right? And so let's suppose that we have a rotation from E1 of amount theta. We have angle theta. Okay. In this setting, you can check this, but it's not difficult to do. You can see that Q as a function of time can essentially be written using this basis as cosine theta function of time, sine theta function of time 0 minus sine theta function of time cosine theta function of time 0, 0, 0, 1. Okay? What this implies is that E equals 1/2, right, 1/2 cosine theta t twice of that 0, 0, 0 cosine theta function of time 0, 0, 0, 1, and you need to have it twice cosine theta here. Okay, it's equal to this, and then of course we subtract twice of the isotropic tensor, right? So we get a -2 here, -2 there, and a -2 there. Okay, all right. Sorry. Sorry, I need to have a 2 here as well. Okay, now we have everything right. Okay? Now, as theta evolves, it's not difficult to see that as theta departs from 0, this term, both the diagonal terms in the 1, 1 and 2, 2 positions turn out to be very non-zero. Okay? Okay, it's not difficult to see, right? If you have an angle of theta equals pi by 4, right? That turns out to be of the order of √2 minus 2. Okay, example. Okay, I just realized that I've been calling this E, but the whole point is that this is epsilon, the small strain tensor, right? Okay, so if theta as a function of time equals pi over 4, okay, what we're seeing is that epsilon 1, 1 equals epsilon 2, 2, which turns out to be 2 over √2 minus 2, okay, which is very different from 0, right? Right? As a result, what we're seeing is that if you use the infinitesimal strain theory to try and model this type of motion, right, you pick up very large strains, okay, And in fact, if you were to do a linear elasticity calculation based on the infinitesimal strain for this type of rotation, what you would conclude is that as a result of this rotation, because epsilon 1,1 and epsilon 2,2 are so different from 0, you would have a tremendous amount of stress developing in the 1,1 and 2,2 directions, right, in plane. And in fact, this body would swell as it rotated if you were to follow the infinitesimal strain theory. Okay? However, when we follow the Lagrange strain tensor, right, the one here, we see that it fundamentally ensures that strains are 0. Okay? This is one of the most important insights that we gain from doing continuum mechanics properly, by doing the kinematics properly. All right. What I'm going to do now is just make one more statement about the polar decomposition, which we've seen in the previous 2 segments, and then we'll end this segment. So we've been calling the polar decomposition that we saw the right polar decomposition. Okay, and this is when we write F equals RU. It's called the right polar decomposition simply because the stretch tensor here appears on the right of this tensor product on the right hand side, right? Because U is the tensor on the right of the product RU. Okay, in the right hand position of the product, right? Or I guess I should say correct, in order that you don't confuse my saying right with the right polar decomposition. Okay, this is why we call it the right polar decomposition. That ought to get you wondering, is there a left polar decomposition? Indeed there is, okay? There also exists a left polar decomposition. Okay, which is that we can simply write F also as the product of a rotation tensor and a stretch tensor, a positive definite symmetric stretch tensor, but this product is written as VR. This is called left because in this case, this is the stretch tensor. Okay, it's called the left stretch tensor. Okay, and for the same reason, U that we've been calling the stretch tensor is also called the right stretch tensor. The rotation tensors involved in the 2 decompositions, the 2 polar decompositions are the same. Okay, it's the same R. Okay, so what we have here is that R belongs to SO3, V belongs to S plus 3, so it's also positive definite. Okay, now just as we saw that U square is related to C, we also have V square equals B, which is called the left Cauchy-Green tensor. Okay, so let me just rewrite that last line here. V square equals B, which has a form similar to C but not quite the same. C was F transpose F, B is F transpose. Okay, what does B do for us? If this is our current configuration and we have a vector here that I'm going to write as epsilon little m, okay, this is an omega t, and if this is the reference configuration omega naught. Right, that's our basis. Now, we can think of, we have the deformation or the motion, okay? We can ask the question, what would happen if we were to somehow try to pull back epsilon m into the reference configuration? We know that some vector went from here to there, okay? We know that some vector went from here to epsilon m. How do we think of this vector as having been sort of pulled back or unstretched from epsilon little m in some sense? Okay? It emerges that the way to think about the magnitude of this vector is that it is epsilon little m B inverse epsilon m. Okay? B inverse, not B. But rather than working with the inverse, people prefer to work with B. So that's why rather than using B inverse to define a stretch tensor, we tend to use B itself. Okay? So B inverse, so epsilon m dot B inverse epsilon little m is the square of the magnitude of the vector in omega naught in the reference configuration whose magnitude when deformed to omega sub t is epsilon m whole square. Okay? So the way this would often be described in the early days of continuum mechanics would be that people would think of the deformed configuration and then say, well, you know, this vector here that I'm pointing to with my index finger, think of how this vector came from something out here. And because of the use of the finger, this tensor B inverse is often called the finger tensor. Okay? So I'm not going to write that. It's called the finger tensor. Just one more property. One can show that the eigenvalues of B are the eigenvalues of C. Okay? And this just comes from the definition of B and C. Okay? It's not difficult as an exercise. It's based upon the fact that the invariants, the principal invariants of B and C are the same. Okay, so the eigenvalues of B are the eigenvalues of C. The eigenvectors are not. Okay? The eigenvectors of B, we tend to write them as n little I going from 1 to 3, okay? And in general, n little I are not equal to the eigenvectors of C, n capital I. And I'll just use that there, okay? In fact, maybe I'll just do this, okay? That better be the case because if the eigenvalues and the eigenvectors of two tensors are the same, the tensors have to be the same, okay? But then their definitions are clearly not the same, okay? And finally, okay, so V admits a spectral decomposition just like U does, and that spectral decomposition turns out to be lambda I Ni tensor little ni, and I'll put the B here to say that the eigenvectors of B and V are the same. Now observe that B, C, U, V, okay, their eigenvalues are related, okay? these are the same lambda i's that appear in the definition of the spectral decomposition of U. The eigenvectors, however, are different. Is there anything else I need to say here? Just one last thing. We're talking about how to write U, V, B, C in terms of these eigenvectors. Can also show the following. You may ask, what about R? Why leave it out? Okay. Can also show R is the sum over I equals 1, 2, 3. Little ni, each eigenvector of B, tensor the corresponding eigenvector of C. Okay, that's sometimes a useful result. Okay, we're going to stop here for this segment, and we're sort of done with our study of the polar decomposition at this point.